Good evening students, welcome back to our Sc. Third year quantum mechanics class. In last lecture, we discussed about the particle in a 1D box, the wave function associated with that particle. After that, we are deriving its eigenvalue, its eigenfunction, and we are getting its eigenfunction psi is equal to square root of 2 by L sin nx. Now, if we move forward, today we are going to find out the average kinetic energy associated with that particle, average kinetic potential energy associated with that particle, and how its momentum is quantized, or expectation value of momentum we have to find out in today's lecture. Now, first I want to find out its average kinetic energy. Our particle lies in between that box, the length of that box is 0 to L. That's why integration 0 to L square root of 2 by L sin kx into minus h cross square by 2m dou square by dou x square, dou square by dou x square. Here our particle is moving, or our box is a 1D box which lies along x direction. That's why y and z components are 0. Y and z components are 0. Therefore, square root of 2 by psi into psi star dx. Therefore, psi into psi star is minus square root of 2 by L sin kx. If we multiply that, therefore, if we take outside the integral, it gives 2 by L k square h cross square by 2m, k square h cross square by 2m into integration of 0 to L sin square kx dx, sin square kx dx. Now, if we simplify this integration, it gives k square h cross square by 2m, k square h cross square by 2m only, because the integration of 0 to L sin square kx dx is equal to, it gives one value, 1 into L by 2. If we cancel that, then it gives k square h cross square by 2m, k square h cross square by 2m, or thus the average value for kinetic energy of this particle is k square h cross square by 2ml square, because if we integrate it within limit 0 to L, then it gives 1 by L square, pi square h cross square by 2ml square. This is the average value for kinetic energy, average value for the kinetic energy. The next, average value for the potential energy. Now, our particle is moving along x direction only within limit 0 to L, but the potential energy of the particle inside the box is 0, at the boundary at x is equal to 0 is infinite, at x is equal to L is also infinite. It means what? Our potential energy varies from minus infinite to plus infinite. Psi star psi dx is equal to sin kx 0 sin kx dx is equal to 0, because the potential energy of that particle inside the box is 0. Then obviously our average potential energy is also equal to 0. Thus the average potential energy of the particle inside the box is 0 irrespective of the wave function. Therefore, total energy or Hamiltonian operator H is equal to pi square h cross square by 2 ml square plus 0. Hamiltonian energy is nothing but the average kinetic energy of that particle, pi square h cross square by 2 ml square. This is the same result obtained from solving eigenvalue equation for the particle inside the box, eigenvalue equation for the particle inside the box. However, if the wave function used were not eigenstate of energy, then we cannot use the eigenvalues approach and need to rely on the expectation value of describe the energy of that system. Okay, that's why these are the average energy. Now next, why momentum is quantized, that we have to find out, or the expectation value of momentum is, which therefore expectation value of p is equal to integration 0 to L, because our the particle is lies along x axis within limit 0 to L only. Therefore 0 to L psi star p psi dx, psi star p psi dx. We know the operator value of p, which is equal to minus I h cross dou by dou x only, because particle is moving along x direction. There is no variation along y and z. Therefore psi star minus I h cross dou by dou x psi dx. If we substitute the value of psi star and psi, which is equal to square root of 2 by L sin n pi x by L minus I h cross dou by dou x square root of 2 by L sin n pi x by L dx. If you multiply square root of 2 by L, 2 by or there is no variation, square root of 2 by L is a constant quantity, that's why we can take outside the integral, which is equal to 2 by L minus I h cross, minus I h cross is also a constant quantity that we have to take outside the integral, minus I h cross 2 by L minus I h cross 2 by L integration 0 to L sin n pi x by L dou by dou x sin n pi x by L dx. Now first we have to differentiate that sin n pi x by L. It gives cos n pi x by L into n pi by L, n pi by L. That n pi by L is a constant we can take outside the integral. Therefore expectation value of p is equal to minus I h cross 2 by L minus I h cross 2 by L n pi by L, n pi by L integration 0 to L, integration 0 to L sin n pi x by L into cos n pi x by L, cos n pi x by L dx. Now integration of sin n pi x by L cos n pi x by L dx is 0. If you solve this integral, it gives a 0. Therefore expectation value of p is always 0. Is always a 0. That's why momentum is quantized. In this case, when particle in a box, in a 1D box, in that case momentum is quantized. Its expectation value is 0. Okay. This is all about the particle in a 1D box, its eigenvalue, its eigen in a function, then its average value of kinetic energy, average value of potential energy, average value of Hamiltonian operator, then momentum quantization of a particle in a 1D box. Okay, this is all about the particle in a 1D box. Now the last point from this third chapter is linear harmonic oscillator. The derivation of this linear harmonic oscillator we will discuss in tomorrow's lecture, but what is my linear harmonic oscillator, that we have to first understand. Okay. First we will discuss its classical concept, then in tomorrow's lecture we will discuss its quantum concept. Actually the simple harmonic oscillator, a non-relativistic particle in a potential 1/2 kx square, is an excellent model for a wide range of system in nature. In fact, not long after Planck's discovery that the black body radiation spectra couldn't be explained by assuming energy to be exchanged in quanta. After that, Einstein applied the same principle to the simple harmonic oscillator, thereby solving a long-standing puzzle in solid-state physics. The mysterious drop in specific heat of all solids at low temperature. The classical thermodynamic, a very successful theory in many ways, predict no such drop. With the standard equation of energy kT in each model, potential plus kinetic, the specific heat should remain more or less constant as the temperature was lowered, assuming no phase change in that case. To explain the anomalous low temperature behavior, Einstein assumed each atom to be independent quanta or simple harmonic oscillator. And just as for black body radiation, he assumed the oscillator could only absorb or emit energy in the quanta. Consequently, at low enough temperature, there is rarely sufficient energy in the ambient thermal excitation to excite the oscillator, and they freeze out just as a blue oscillator do in low temperature black body radiation. Einstein's fixture was later somewhat refined. The basics set of oscillator was taken to be standard sound wave oscillation in this solid rather than individual atom, it making the picture even more likely black body radiations in a cavity. But the main conclusion, the drop off in specific heat at low temperature was not affected. All that kind of loopholes in solid state physics was explained with the help of classical simple harmonic oscillator. A simple realization of a harmonic oscillator in classical mechanics is a particle which is acted upon by a restoring force proportional to the displacement from its equilibrium position. Consider motion in one dimension. This means F is equal to minus kx. Such a force might originate from a spring which obey a Hooke's law, as shown in this figure. According to Hooke's law, which applied to the real spring for sufficiently small displacement, the restoring force is proportional to the displacement, either stretching or compressing on both sides from its equilibrium position. Okay. Now, applying a Newton's second law to the force, therefore F is equal to m dou square x by dou x square minus kx, or F is equal to minus dou v by dou x. From this equation, V is equal to 1/2 k square. This is the kinetic energy associated with that particle, which has the shape of parabola. This potential energy gives a shape of parabola. A simple computation shows that the oscillator moves between positive and negative tuning points, that is plus or minus x, where the total energy E equals to the potential energy 1/2 kx square max, while the kinetic energy is momentarily 0 in contrast when the oscillator moves at x is equal to 0, and the kinetic energy reaches its maximum value while the potential energy is equal to 0, vice versa. Where the kinetic energy is maximum, at that point potential energy is 0, where the potential energy is maximum, at that point kinetic energy is 0. This is the classical view of harmonic oscillator. In tomorrow's lecture, we are going to solve a derivation for a harmonic oscillator. Okay. If you have any doubt related with this, you can ask me anytime. Okay. Thank you.